Special relativity. Can we trap a train in a tunnel shorter than the train? A train is moving at 0.8 c relative to frame k. The length of the train in its own frame k prime is a equals 120 c meters. A tunnel entrance is located at distance b equals 1000 c meter from the origin of frame k. The length of the tunnel in frame k is d equals 100 c meters. When does the end of the train reach the entrance of the tunnel? We compute Lorentz factor gamma. Gamma equals 1.6667. At point A, we apply the spacetime transform. The end of the train reaches the entrance of the tunnel when x prime a equals 0, and x a equals b equals 1000 c, at time t prime a relative to k prime and time t a relative to k. Substituting that in the spacetime transform at point A, we obtain computing clock time t prime a equals 750 seconds. Computing clock time ta equals 1250 seconds. Clock time ta and clock t prime a readings when end of the train reach the entrance of the tunnel are shown in the underneath drawing. Where will the front of the train be when the end of the train reaches the entrance of the tunnel? Since we are taking snapshot in time in frame k and the observation is taking place in frame k, the clocks in k are synchronized, hence tb equals ta equals 1250 seconds. At time tb equals ta equals 1250 seconds, the front of the train relative to k prime will be at x prime b equals a. We apply the spacetime transformation at this point b. Substituting x prime b equals a equals 120 c meters and tb equals 1250 seconds in the spacetime transform at point b, we obtain time t prime b equals 654 seconds. Clock t prime b reading when end of the train reaches the entrance of the tunnel are shown in the underneath drawing. Clock tb readings when end of the train reaches the entrance of the tunnel are shown in the underneath drawing. The front of the train will be at coordinate xb equals 1072 c meters. The length of the train as measured by observer k is xb minus xa equals 1072 c minus 1000 c equals 72 c. The front of the train coordinate xb at time 1250 seconds is shown in the underneath drawing. What is the length of the train as measured by observer k? We can apply the law of length contraction which will give us the same results. xb minus xa equals 72 c. The length of the train as measured by observer k is shown in the underneath drawing. When does the front of the train reach the exit of the tunnel? The front of the train reaches the exit of the tunnel when x prime d equals 120 c and xd equals 1100 c at time t prime d and td. Substituting. The time t prime d equals 675 seconds. Clock t prime d readings when end of the train reach the entrance of the tunnel are shown in the underneath drawing. Clock td readings when end of the train reach the entrance of the tunnel are shown in the underneath drawing. When the front of the train reaches the exit of the tunnel, where will the end of the train be? When the front of the train reaches the exit of the tunnel, the end of the train will be at x prime c equals 0 at time td equals tc equals 1285 seconds. We apply the spacetime transformation at this point c. Substituting. The time t prime c equals 1285 times 0.6 equals 771 seconds. The location of the end of the train relative to k is xc equals 1028 c. Clock T'(C) readings when end of the train reached the entrance of the tunnel are shown in the underneath drawing. Clock T'(C) readings when end of the train reached the entrance of the tunnel are shown in the underneath drawing. The end of the train will be at coordinate xc equals 1028 c. The distance between the end of the train and the tunnel entrance is therefore 1028 c minus 1000 c equals 28 c. Note that, in relativity, we can add or subtract distances on the same axis in the same frame only. We cannot add or subtract distances between axes which belong to two different frames k and k' moving relative to each other, such as axis x and x'. What is the period of time between the moment at which the end of the train coincide with the entrance and the moment at which the front of the train reach the exit? The end of the train coincide with the entrance at time 1250 seconds and the front of the train reach the exit at time 1285 seconds. Hence, the time interval between the moment at which the end of the train coincides with the entrance and the moment at which the front of the train reaches the exit is 1285 minus 1250 equals 35 seconds. The order of events for observer K and K'. According to observer K, the end of the train reaches the entrance of the tunnel at time t equals 1250 seconds, and after that the front of the train reaches the exit of the tunnel at time t equals 1285 seconds. And the time interval is delta t equals 35 seconds. But as for observer K', the end of the train reaches the entrance of the tunnel at time t' equals 750 seconds, and before that the front of the train reaches the exit of the tunnel at t' equals 675 seconds. And the time interval between the two events is delta t' equals negative 75 seconds. So how could these two events happen in different order for two observers? When we studied the sequence of events from the standpoint of K, we assumed that his clocks were synchronized to establish comprehensive observation for all events. As a result, the clocks in frame K' were assumed to be non-synchronized. So to establish comprehensive observation for all events for observer K', we have to see all events at the same time from frame K' standpoint. At time t' d equals 675 seconds, the train front reaches the exit of the tunnel. Therefore, to see all events at the same time from K' standpoint, we have to assume that all clocks in frame K' are synchronized. At time t' d equals 675 seconds, we will assume that all clocks in K' are synchronized, and the front of the train is at the exit of the tunnel. In this case, t' d equals t'(C) equals 675 seconds. So where will the end of the train be relative to K? We apply spacetime transformation at point C, where x'C equals 0, t'(C) equals 675 seconds to find the coordinates x, c and tc. Substituting, the location of the end of the train relative to K is xc equals 900 c. We obtain time tc equals 1125 seconds. Clock reading tc and coordinate xc are shown in the underneath drawing. And where will the end of the tunnel be at t'(C) equals t'(E) equals 675 seconds relative to K'? At time t'(E) equals 675 seconds, and xe equals 1000 c, we apply the spacetime transformation at point E. Substituting, from which we compute x'E equals 60 c. And that is at time t equals 1205 seconds. Clock reading and TE and coordinate x'E are shown in the underneath drawing. This example explains why observer K' sees events in different order. Observer K' sees that when the front of the train reaches the exit of the tunnel, the end of the train is still outside the tunnel. The length of the tunnel as measured by K', x'd minus x'E, equals 120c minus 60c equals 60c, which is consistent with the law of length contraction. Delta x prime equals delta x times 1 over gamma. Notice that the factor 1 over gamma is multiplied with the length measurement delta x in the frame where the clocks are not synchronized. At time t prime a equals 750 seconds, we will assume that all clocks in k prime are synchronized, and the end of the train is at the entrance of the tunnel. In this case t prime a equals 750 seconds. So where will the front of the train be relative to k?
We apply space-time transformation at point G, where x prime G equals 120c, t prime G equals 750 seconds to find xg and tg.
Substituting, we obtain at time t prime f equals 750 seconds, and xf equals 1100c, we apply the spacetime transformation at point f. Substituting, we obtain x prime f equals 60c, tf equals 1330 seconds. The reason why an observer sees contraction of length is because he is observing the difference in space between two non-synchronized events in another frame. The front of the train relative to k is shown in the underneath drawing. At time t prime a equals 750 seconds. The front of the train is located inside the tunnel but in the past, and therefore at time t prime a equals 750 seconds, the front of the train will be outside the tunnel. At time t prime d equals 675 seconds. The end of the train is located inside the tunnel but in the future, and therefore, at time t prime d equals 675 seconds, the end of the train will be outside the tunnel. The best way to understand the train problem and length contraction is by studying the relation between special relativity and spiral field theory.